everyone. In today's video session, we'll be learning how to perform heat transfer analysis using finite element method. Also, we'll try to find the temperature distribution in a composite wall using this method. I am Dr. Bharat from Global Academy of Technology. Let us understand few basics of heat before going into the direct analysis. Heat is the energy in transit. It is considered as a low-grade energy because the heat is a result of movement of tiny particles within a component. Whenever an object is heated, the heat energy will be converted into kinetic energy within the molecules, and this high kinetic energy molecules will transfer its energy to the next adjacent molecules, thus transferring heat from the current molecule to the next molecule. The heat transfer rate is represented by Q and will be having a unit of joule per second. Heat transfer rate per unit area is called as heat flux with a unit of watt per meter square. There are three modes of heat transfer: conduction, convection and radiation. The rate equations of these three modes are as shown on the screen. In case of conduction, K is known as thermal conductivity with a unit of watt per meter Kelvin. In case of convection, H is called as convective heat transfer coefficient, and in case of radiation, sigma is known as Stefan-Boltzmann constant. Let us discuss few basics about heat transfer through conduction. Heat transfer always goes with a law of conservation of energy, which states that the heat into the body plus the heat generated will be equal to the heat going or moving out of the body plus rate of increase of internal energy, which is nothing but the work done. The entire heat transfer is based on this equation, and using this equation we can also determine the three-dimensional heat conduction equation as shown here. The governing equation in case of finite element analysis is given by the following equation. In this equation, K represents the thermal conductivity matrix, H represents the convection matrix, T is nothing but the temperature distribution within the system, and Fc and Fq are the load vectors. In this case, Fc represents the convective load vector as well as Fq represents the load vector due to heat generation. This is the governing equation or equilibrium equation which we'll be using while performing the analysis. The conductivity matrix K is given by the following equation. This equation is in analogous with the stiffness matrix in case of bar elements. In this equation, K is called as thermal conductivity, A is called as the area normal to heat transfer, and L is known as the thickness of the wall. The equation for convection matrix depends on the location where exactly convection is happening. For example, in this diagram, the convection is happening at the left side of element 1, that is at node 1. Thus, a value of 1 will be added to the corresponding diagonal element. So in this case, the value of 1 is added at node 1. Similarly, in this diagram, convection is happening on the right side of element 1. So the corresponding value of 1 will be added in the heat convection matrix at node 2. Thus, depending on the location of the convection, the matrix equation for convective matrix will keep on changing. Similarly, the load due to convection also depends on the location of or the position of convection. In the first case, since the convection is happening towards the left side, So a value of 1 is added at the first node. And in the second diagram, since the convection is happening at node 2, a value of 1 will be added at node 2. In these equations, A represents the area normal to the heat transfer, H represents the heat transfer coefficient, and TA represents the ambient temperature. The load due to heat generation is given by the following equation. In this case, Qg is the heat generated in the system with the units watt per meter cube. Let us now perform heat transfer analysis through a composite wall using the given example. In this example, the temperature distribution through a composite wall has to be determined. The wall thickness of each one has been given along with its respective thermal conductivity values. Also, the heat transfer coefficient and ambient temperature has been given such that on the left side of the composite wall there is convection. Towards the right side of the composite wall, a boundary condition where the temperature of 20 degrees has been imposed. This structure has got two elements with 3 nodes. Let us now perform finite element analysis to determine the temperature distribution through the composite wall. Let us begin our analysis by finding a conductivity matrix. The conductivity matrix is given by the following equation. With the given values in the problem as K1, A1 and L1 and K2, L2 and A2, and substituting these values in the conductivity matrix, we will be able to determine the conductivity matrix for element number 1 as well as for element number 2. After finding the conductivity matrix, these two matrices are assembled as shown. The first matrix represents the first element as well as the second conductivity matrix represents the second element. The unfilled rows and columns will be filled with zeros. Thus, we will be able to determine the global conductivity matrix for the entire structure. Once the conductivity matrix has been determined, we will be now finding the convection matrix. The element convection matrix is given by the following equation. It depends on the location of convection. In this example, the convection is happening at the left side of element 1, or we can say that convection is happening at node 1. Since it is happening at node 1, a value of 1 is given in the first diagonal of this matrix. By substituting the given values of area as well as heat transfer coefficient, we will be able to determine the value of convection matrix of element number 1. The convection matrix of element number 2 is represented by this equation. If we closely observe element number 2, there is no convection next to this element, neither at the left side of this element number 2 or at the right side of this element number 2. There is no convection. Since convection is not there, the convection matrix for the second element will be zeros. Now, after finding the convective matrix of each element, let us now assemble both the convective matrix to obtain the global convective matrix. Thus, a global convection matrix is obtained by assembling the individual convection matrix of each element. The governing equation for heat transfer analysis is represented in this form. This equation can also be represented such that we can add the conductivity matrix as well as the convection matrix. Let us now add the conduction matrix with the convection matrix. After finding the values of K and H and later adding it, let us now determine what will be the load on this system. There are two types of loads which we need to determine: load due to convection as well as load due to heat generation. Since in this example there is no heat generation, the component FQ will be 0. Let us now find the value of load due to convection. The load due to convection is represented by the following matrix. FC is equal to AH TA multiplied by the matrix 1 and 0. In this case also 1 will be at node 1 because the convection is happening at node 1 as shown in the figure. By using the values of H, A and TA, ambient temperature or bulk temperature, in this example we will be able to determine the load due to convection for element number 1. Similarly, the load due to convection at element number 2 will be 0 because there is no convection at either left side or right side of element number 2. Once you have found the convection matrix for element number 1 as well as element number 2, let us now assemble these two matrices to find the overall load due to convection for the entire system. This will be the total load for the entire system. We will be using this load in the governing equation to determine the temperature distribution through the composite wall. As said earlier, the load due to heat generation will be 0 in this example. Therefore, the total load will be the convective load itself. Substituting the values of the conductivity matrix, convection matrix, load due to convection in the governing equation, we will be now able to determine the values of the temperatures. One of the boundary conditions in this example has been given such that the value of T3, that is at node number 3, is given. Since the value of T3 is given, the corresponding row and corresponding column will be eliminated as shown in this matrix, and also the force will be modified. In this case, since T3 is known, the corresponding third row as well as third column will be eliminated and the force matrix will be modified by the following equations. In this case, K13, K23, K33 represents the corresponding conductivity elements at column number 3. These values has to be multiplied by the known value of temperature. In this case, the known value of temperature is T3, that is nothing but 20. By eliminating and also by modifying the force matrices, we will be obtaining a 2 cross 2 matrix, by solving which we will be able to determine the value of T1 and T2. Thus, we will be able to determine the temperature distribution through a composite wall subjected to both conduction as well as convection. Let us now see one more example. In this example, a composite slab with 3 different materials are given. The thermal conductivity of each material is given, as well as the thickness of each material has been given in the numerical. Also, we can see that there is a convection happening at the left side of element number 1, and there is a imposed boundary condition of 20 degrees which has been given at the right side of element number 3. Also, the heat transfer coefficient and the bulk temperature has been given in this numerical. Let us now solve this example to determine the temperatures at each corner of the wall. So as usual, to start with the problem, let us start with finding the conductivity matrix K and for each element, and we will be assembling this matrix to obtain overall global conductivity matrix for the entire structure. By using the given values in the numerical, we will be finding the conductivity matrix for element number 1 as well as for element number 2 and element number 3. These three values or these three matrices will be assembled to obtain the overall conductivity matrix. In this example, since there are 4 nodes, the total conductivity matrix will be a 4 cross 4 matrix. Let us now assemble the each elemental conductivity matrix to obtain the global conductivity matrix. The first matrix, the second matrix, as well as the third conductivity matrix for the third element are assembled as shown, and the empty rows and columns will be filled with zeros. This will be the final conductivity matrix for the entire structure, which is a 4 cross 4 matrix depending on the number of nodes. Let us now determine the convection heat transfer matrix. The convective heat transfer matrix is given by the following equation: A into H multiplied by the matrix. One can observe that there is a particular reason for adding 1 here, because the convection is happening at node 1. So at the first element, 1 will be added to the equation. The convection matrix for the entire structure will be also a 4 cross 4 matrix, which will be given as A into H multiplied by the matrix as shown. The value of A and H as given in the problem is substituted to obtain the global convection matrix. Let us now add the conductivity matrix as well as convection matrix to obtain the total matrix. Let us now find the load due to convection. In this case also, convection will be happening at the left side of element number 1. So the convection matrix equation will be AH T infinity 1 and 0. The values of A, H and T infinity or TA is given in the numerical, so that by substituting these values we will be able to determine the load due to convection. The load due to convection will also be a 4 cross 1 matrix, that is, it has got 4 rows and 1 column. Load due to heat conduction or heat generation will be 0 in this case, because in this example they have not mentioned anything about the heat generating elements. Therefore, FQ will be 0. So the total load will be FC. The total load will be the load due to convection itself. Now, by substituting the value of conductivity matrix, convection matrix and load due to convection, we will be able to determine the temperature distribution in the composite wall. An imposed temperature boundary condition has been given in the numerical, saying that the temperature at node 4 is 20 degrees. Thus, there is a temperature of 20 degrees in this equation. Since the fourth temperature is known, that is, the temperature at node 4 is known, the corresponding column and the corresponding row will be eliminated. Once these values are eliminated, the force matrix or the load matrix will be modified by using the following equations. In this case also, the values of K14, K24, K34 and K44 represents the corresponding elements in the fourth column, as well as the temperature is nothing but the value of T4. With the given values of force and temperature, we will be able to reduce the 4 cross 4 matrix into 3 cross 3 matrix. The 3 cross 3 matrix will be as shown in the following equation. By solving this equation, one can be able to determine the value of T1, T2 as well as T3. With the knowledge gained in the previous two examples, the viewers can practice the problem given on the screen. In this example, a brick wall of thickness 0.3 mm and with a thermal conductivity of 0.7 watt per meter degree Celsius has been given. The inner surface is at 20 degrees Celsius and the outer surface is at minus 15 degrees Celsius, which is exposed to cool air. The heat transfer coefficient associated with the outer surface is 40 watt per meter square degrees Celsius. We need to determine the temperature distribution as well as heat flux through the wall. Understand that unlike other problems, the diagram for this numerical has not been given. Viewer has to understand and draw the diagram. Also, there is a condition that the single plane wall has to be modeled by using two elements. Thus, each element will be having a thickness of 0.15 mm. Also, the inner surface, that is one of the surface, is subjected to a temperature of 28 degrees Celsius and the outer surface is subjected to convection. So thus, by using the previous knowledge, try to solve these examples. Thank you friends for watching this video. We'll be meeting in my next video session where we'll be learning the heat transfer analysis through fins using finite element methods. Thank you. Have a nice day.